Here I just want to take a pause and remind you this stuff is all imaginary. Okay, populations imaginary. They're not firmly defined. Probability also imaginary. You're never going to go out there and touch a real probability in the world. These are analytical tools. They help us think about what's going on and reason about real problems, but they themselves are not real. I mean, if you want to back up even further, like numbers aren't real either. Okay, like go out there and find me the number two in the real world. It's made up. So people are often confused about probability and populations because these things are not real. They're abstractions. Like, okay, how can this help? But nobody seems to be confused about the way that the number two is helpful, or the way that the number five is helpful, or the way that addition is helpful, even though those things aren't real either. So, there's a lot of stuff that we work with that's totally imaginary, but is really just an analytical tool. Just remember that, keep that in your head. Um, okay, so we never really know these things. We can't ever measure their full population. They're abstract ideas. Don't forget. Okay. This is again the case with numbers, with every other mathematical description of reality that we have. All of physics, all of it's made up. Okay. It is a made-up tool that helps us solve real problems in the real world. So probability, by the way, this is an example of something that we'll come back to later in the course, which I like to call an estimand. Some people call a parameter. But an estimand is just some quantity about the population, usually the quantity that we want to know, the thing that we're interested in. So, for example, the mean age in a population would be an estimand, because it's an average, but it's the average in the population. Or a probability, which is a count in the population. An estimand is basically just some characteristic of the population. We'll come back to this a bit later, but probability is one example of that. So speaking of how this stuff is imaginary, and it's all in reference to a imaginary population, let's extend our notion a little bit of what we mean by population, so you can see how this might be used in a more flexible way than literally just talking about people and groups. Let's say that you imagine taking random samples of 3 people from the population. So here's my people population, and now I'm going to randomly pick 3 people and put them in this little box over here. I'm going to repeat that process, randomly pick another 3 people. This is with replacement, so I'm putting everyone back after I pick them. And I do that a lot, maybe forever. So I end up with these little boxes, each of which have 3 people. So this is not a partition. I haven't uniquely put each person in their own box. A person can appear in multiple boxes. Now what we have is a population of samples. So instead of my population having individuals in it, each individual in the population is a possible sample that I could have drawn from my population. But each sample has characteristics, just like an individual does. So in my original population, we had the pink people and the black people and the hat people. Now in this population of samples, I could say that the samples have different characteristics, like what's the proportion of pinkness in the sample. So you can either have 1/3, 2/3, or 3/3. So you can just treat these samples as like individuals that have these different characteristics, and then you can ask about probabilities defined in this population of samples. You can say, what's the probability that I get a sample that has 2 pink people and one black people, right? And that, again, conceptually is just the number of samples that are like that over the total number of samples that you have. So these probabilities, they're abstract ideas. We can reason with them and guess about them. They're not things that we can physically measure, but you can see here that this abstraction is actually quite powerful. We can talk about a lot of things, not just groups. So let's go through this one here. Again, pause this, work on it yourself. Let's say that the probability of being diabetic in New Zealand right now is 1 out of 10. And I survey 100 random New Zealanders, and I repeat that 1 billion times. So I have 1 billion different samples, each sample having 100 people. Again, not necessarily those groups are exclusive. Somebody might appear in multiple samples. The same person might appear in multiple samples. And now I have this population of surveys. So these questions are conceptual. There's not really math here. I just want you to think about them. First one is, would you expect to have any surveys where we got exactly 10 diabetics, 10 out of 100? And how many? I mean, a few, a lot? What do you think about that? And then the second question is, in roughly what proportion of surveys would you expect to get more than 10 diabetics? And again, don't do any math here. There's nothing that you can do. It's just a conceptual question. So for the first one, I mean, I would say, there are going to be surveys where you get exactly 10 diabetics, right? If you're grabbing 100 people, there's some chance that exactly 10 of them are diabetic. Of course, there's also a chance that you get 11, that you get 12, right? There is some chance that you get really unlucky, and every one of those 100 people that you sample is diabetic. There's a chance that you get really unlucky, and none of them are diabetic, right? All of those are possible, not necessarily likely, but possible. You can quantify exactly how likely it is using the kind of probability tools that we've been talking about, if you wanted to. But similarly, the next question is asking about, in what proportion of surveys would you expect to get more than 10 diabetics? I would say you should think it's like about half, right? Because if the population rate of diabetes is 10 out of 100, or 1 in 10, then you should expect on average you're getting 10 diabetics, but sometimes you'll get more, sometimes you'll get less, right? Is there any reason why you should be getting always more than, or is there, or always less? I don't particularly think so. So I would figure that the chance that you get more than 10 diabetics, roughly speaking, should be about equal to the chance of getting less. Again, it's not actually quite that. You can work these things out exactly with already what you know, but the point of this is just to think conceptually the difference between population and sample, and the fact that your sample is random. Sometimes you get lucky, sometimes you get unlucky, and you're not actually really measuring that true population probability. So, for example, let's say you see a survey that somebody does, and they found 13 diabetics out of the 100 people that they surveyed. And let's say somebody else, the previously known rate, like we said, is 1 out of 10 or 10 out of 100, same thing. So let's say after this new study, somebody says, hey, we got 13% instead of 10%. So that means that the rate of diabetes has gone up in New Zealand. So my question to you is, do you believe them? What's wrong with that argument conceptually, if anything? I would say, again, without even doing the math, there's a fairly good chance that you're going to find 13 diabetics in a sample of 100, even if in the broader population, the rate is really 10 out of 100, right? So this is, again, illustrating the difference between population, which is what you want to know, and sample, which is what you happen to have. So claiming that the population rate of diabetes has gone up because you have one relatively small sample in which the rate is higher than what you might expect, not particularly justified. Of course, how unjustified is that is precisely the kind of question that we would want to be able to answer with statistics, and that's exactly what we can do with the kinds of probability rules that we're learning right now. So, for example, would this still be wrong if they had found 20 diabetics? If in their survey it was double the rate, right? And what if their sample were 1,000 people and they found 130 diabetics, right? How would that change the way that you reason about this? Intuitively, I mean, I think if they found 20, if they found 50 diabetics in a sample of 100, what's the chance of that if the real rate is only 1 out of 10? That becomes very, very unlikely. It's still possible, but very, very unlikely. And so there probably is something going on. The rate of diabetes probably has increased or something. And again, you can quantify the likelihood of that being the case. Similarly, if it were in a sample of 100 people, but you sampled 1,000 people or 10,000 people, and you were finding consistently higher rates of diabetes, you're more likely to believe that then something's actually going on in the population and it's not just you got lucky or unlucky with this particular sample. So we'll get a lot more into this in the kind of couple weeks later in the course, but I would just want to give you a preview of what is really the fundamental ideas in statistics and how those relate to probability.